Let's look at this problem. The wheel shown in the figure has a weight of 30 pounds, radius of gyration of 0.6 feet. It's attached to a spring, which has a stiffness of 2 pounds per foot, unstretched length of 1 foot. If the disc is released from rest in the position shown, so make sure you can visualize, right? Initially, it's right here. Initially, it's in the position shown. It's released from rest. It rolls without slipping. It's going to come over here, and this is going to be its final position right here. Determine its final angular velocity when g has moved 3 feet to the left. All right, we will use conservation of energy, right? V plus T plus any non-conserved work equals V plus T final. And again, each of these kind of has two terms that it could be. And I like to go ahead and write out the whole thing, right? MGH, 1/2 kx squared, 1/2 mv squared, 1/2 I omega squared, FD m theta equals all this final. MGH final 1/2 kx squared final 1/2 mv squared final 1/2 I omega squared final. And this is the h, the height of point G, the velocity of point G, the I of G, the height of G, velocity of G, I of G. G is already labeled G right there, but G is the center of the whatever has mass in our object. So in this case, the center of the wheel right there. Okay, so we've got that whole equation written out. Don't get overwhelmed by it. Just take it in bite-sized pieces. Was it released from rest? So, many of these problems are released from rest, so the velocity of g and the omega of that object would be 0. Are there any forces that act a distance? No, I don't see any forces drawn on here. The normal force doesn't really act a distance. Yes, there actually could be friction, but it's not kinetic friction. It's static friction. So anyway, there's no FD in this equation. There's no m theta in this equation either. And so this is kind of what it boils down to. All right, let's think about this MGH. A lot of times I like to set my ground, if there is a ground, I set my ground, as the ground. But do you see why don't we just go ahead and set it right here? It starts at 0 and it ends at 0. It starts at 0 and it ends at 0. And so they just have 0 on both sides. Do you see how if I had said this h is 0.75, but this h is also 0.75, these two would add up, would cancel each other out on the left-hand side and the right-hand side of our equation. If there's no change in height, then there's no change in MGH. There's no need to put an MGH in your equation, right? So anyway, if there's no change in height, let's just set that to be our 0 height. All right, there is a spring. I think it is being stretched or compressed. All right, so 1/2 K to pounds per foot times x squared. X is the amount of stretch or compression. Its unstretched length is 1 foot. So if this spring had a length of 1 foot, then its x would be 0. It would not be stretched or compressed. Can you tell this starting length is 5 feet. Starting length is 5 feet. Now I'm not going to put 5 down here. I'm going to put 4, right? 4, because this is the amount of stretch. It is being stretched by 4 feet, right? Length minus your unstretched length would give you the amount of stretch. Okay, I should be more careful with my units, but everything's in feet, pounds per foot. Also, my gravity is going to be in feet if I need it. So I'm leaving off my units. That's all I have on the left-hand side. I don't know if you can tell, but all of the energy is stored in that spring on the initial, the left-hand side of my equation. Now some of it is going to get converted to maybe to kinetic energy, to rotational energy, things like that. All right, on the right-hand side of my equation, 1/2 K x squared. What would be the amount of stretch or compression afterwards? Well, the final position, my spring, the final length of my spring would be 4 feet, but I'm not going to plug in 4 feet right here. I'm going to plug in 3 because that would be stretched by 3. If it's unstretched, length is 1. So 3 would be the amount of stretch plus 1/2 m. This has to be m, not mg, not the weight. And a lot of times in English units, they give us the weight. This is 30 pounds force. We're going to have to do 30 divided by 32.2. Now, I'm not going to go into these units. It's really like a slug. This is feet, and everything else needs to be in feet. This needs to be in feet per second in order for my units to work out very easily. So I'm just going to say 30 divided by gravity, right? M is equal to weight divided by gravity. All right, times V of G squared. I don't think I know that when it's in its final position. Plus 1/2. The I was given as a radius of gyration. Right? Remember, radius of gyration, I is k squared times m. Right? K squared times mass. And this k is the k of the radius of gyration, not the k of the spring. So this would be 0.6 squared times mass, 30 over 32.2. That 0.6 has to be in feet. Everything has to be in feet. If you got something in inches, I would just convert it to feet if I were you. So that's the I, then omega squared. That one equation has two unknowns. Doesn't that happen a lot? Can you figure out Vg equals R omega, right? Vg and omega are related. Vg equals R omega. R is the distance that G is away from the center of rotation. Now, the center of rotation is not like up here. It's not just rotating about there. We're looking at this disc. What is this disc rotating about? Well, the disc is not rotating about its center. This is a wheel that is rolling without slipping. We've talked a little bit about wheels. I don't think we actually did this, but for wheels, where is the instantaneous center of a wheel? Where's the place on the wheel that has zero velocity? Down here on the ground. There's my instantaneous center of zero velocity. So this R, the distance that G is away, G would be right here, and the instantaneous center would be down there at the bottom. R would be 0.75. Vg is 0.75 omega. Plug that in right there, solve for omega. See if you get 4.04 radians per second. This one, just visualizing, I would need to visualize it to tell it's rolling, it's rotating counterclockwise.